So a numerical summary of data, so usually a statistic, but could be a parameter as well, is said to be resistant if extreme values, either very large or very small, do not affect its value substantially. So the extreme value that we saw on the previous slide was 130 because it was a lot larger than all of the other ones. You can technically have an extreme value that's very small compared to the other ones as well. But either way, extreme values, when you throw in extreme values, if it doesn't change it substantially, then it's going to be considered resistant. So it might move a little bit, but it's not going to have that big of a change to it. So it's resisting those extreme values. So let's write this down maybe underneath of it, because I didn't leave a spot for it for some reason. So if we look back at our previous slide, so originally we had the median was 23, so I'm looking at the median right here. Once we had the new hire, it went up to 24.5, so it increased by 1.5 minutes. So it did increase, but it really didn't increase all that much. So the median is actually going to be a resistant statistic or parameter. So median is resistant. And what that means, based on our definition, is that extreme values the value very much. So you've got this 130 number that's a lot larger than all of the other ones, and so it's going to be increasing our the parameters a little bit. The median is resistant, so it's kind of resistant to that change. It's kind of holds still to where it is. It does budge a little bit, but really not all that much. If you look at the mean is not resistant. Okay. So if you look at the mean, here it was about 25, it goes all the way up to 38. So it increased by like 13 minutes, which is a lot more than the 1.5 that we saw for the median. So the mean is going to be more susceptible to those extreme values. So think of it like peer pressure. The median maybe will budge a little bit, but it kind of sticks its ground. The mean, it's just going to be pulled to wherever that extreme value is. So the mean is not resistant, so it kind of gravitates toward the extreme value. So wherever that extreme value is, whether it's large or small, the mean is going to kind of be pulled towards that extreme value. The median's going to move, it's going to budge a little bit, but it's really not going to move too far. And that's always going to be the case, so you don't have to go through for each problem and figure out which is resistant, which is not. By definition, the median is always resistant, the mean is never resistant. Okay. So you don't have to go through and do this example to try to figure out which one is which. This is always going to be the case. And we'll talk about it more with 3.2 with measures of distribution as well, which ones are resistant and which ones are not. Okay, so then they have some examples where they ask you if you look at just what the distribution looks like. We talked about distribution last time. And how you can tell where the mean and the median are. So if you look here in the middle, I'm going to do the middle one first because that's the easiest one to see. So you've got this one where it's symmetric. You've got a nice little bell curve right here. The mean and the median are going to be right in the middle. That's technically also where our mode is going to be, but we haven't talked about mode. But your mean, median, and your mode are just right here, right in the middle, right next to each other. And that happens when it's symmetric. Okay, if we come over here on this side where it's skewed right, Remember with this one it's skewed right because the tail is to the right. Whenever you're talking about things being skewed, you want to look to see where your tail is. So for this one, your tail is to the right. That's where your extreme values are. So you've got a little curve here, but then you've got these outliers over here that kind of don't fit with the other ones. These ones are going to be a lot larger than what we see over here. So the tail over here, that's where you're going to see your extreme values or your outliers. So grab this one. I can't write on that for some reason. So if you have something like this, this is where your tail is. That's where your skew is. And that's where your extreme values are, or your outliers. We're going to talk about outliers later. Those are your extreme values. They're going to be over here. So what's going to happen is if this started out symmetric, but then we threw in these ones, your mean and your median should be right here in the middle, but because we have these extreme values, they're going to be pulled over towards those extreme values somewhere. Your median is going to shift over a little bit towards those values, but it's not going to move all that much. Your mean is going to be the one that's more susceptible to it. So the mean is going to be pulled even farther out towards your outliers. So the mean is going to shift this way towards where your outliers are, where the tail is. So whenever it's skewed to the right, your mean is going to be larger than your median because your mean is going to go towards where these extreme values are. And then on the left, we have the other side, yeah. So if it's skewed left, here we go. It's not a very good curve. Fix that. Like that. So here's where your skew is over here on the right. That's where your tail is, and that's where your extreme values are. And your mean, so your mean is going to gravitate towards where those extreme values are. So instead of your mean and your median being right here at the peak where you want it to be, they're going to be shifted over a little bit. Again, your median is going to shift a little bit. It's not going to stay exactly the same, but your mean is going to go over quite a bit. So your mean, if it was symmetric, it would be right here, but since you have these extreme values, it's going to go over towards them. So with this one, your mean moves towards these outliers. Your median does move a little bit, but it's still pretty close to the middle right here. So in that case, your mean is going to be a lot smaller than your median. So quick do an example. Bar is 32.8 and M, our mean, is 49.1. What is the shape of the distribution? So without knowing any of the values, any of the data values, and we're not able to graph it or anything like that, these are our two values here, X bar and our median. We can figure out what the shape of the distribution is just by knowing those two things. So if we graph what this looks like, say this is 20, 30, 40, 50. So 32.8, maybe like right here, that's my X bar, that's my mean. And my median is 49.1. That's going to be all the way over here. There's my median. Okay, so they're not really close to each other. It's not going to be symmetric where they're roughly equal to each other. So it's going to be skewed which way? Which way do you think? It's going to be skewed one way or another. Which way do you think it will be skewed? To the right or to the left? Right. So left, the mean gets moved over here. This is where my extreme values are, which means that's where my tail is going to be. So this one is going to be skewed left. Without even graphing it or knowing what our raw data values are, just because our mean is so much smaller than our median, we know it's going to be skewed left. Those are a little tricky. Oh, we do have another example, sorry. Well, I guess I kind of jumped the gun. All right, so for this one,